right, welcome to CS50. This is week 4. So it's always kind of fun when you pick up the paper in the morning and there's actually something apropos to class that day. And this is an article on the front page of today's Wall Street Journal. And those of you who have a computer know that your computer has a keyboard, but it's called a QWERTY keyboard for some reason. Why is it called a QWERTY keyboard? OK, I can't actually make out any of those comments, but presumably it's because it spells QWERTY, Q-W-E-R-T-Y. Here's a random keyboard from the internet, Q-W-E-R-T-Y. If you've never heard this expression, you have a QWERTY keyboard just because that's the most phonetically pronounceable string of characters someone discovered many years ago. But there's this alternative called Dvorak, which some people, perhaps those among those more comfortable, sometimes use. Personally, I never got the hang of this, but this article here in the Wall Street Journal is about this. And quick little excerpt, which amused me. The Dvorak keyboard layout, though around for decades, is as little known among the general typing population as it is passionately embraced by its devotees. It is to the keyboard what Esperanto is to language and what Betamax is to videotape. Fans say it lets them type at blazing fast speeds with less strain on their hands and wrists than typing on a conventional keyboard. And this was, I thought, the punchline. Nobody else cares. And if you actually then follow up, let's see, turn to page A4. There's more discussion on this. And the context was there's a bunch of people sort of bemoaning the fact that smartphones these days, iPhones and whatnot, apparently don't support Dvorak. They've kind of optimized for the rest of the world. The Wall Street Journal really went to town on people here. Smartphones seem dumb to Dvorak fans. But let's see. This was kind of cute. So the final quote in this article is, I think it's really sad, says one Dvorak devotee, that Dvorak isn't on smartphones because it's something, but it's something I'll have to live with. I'm a Dvorak typist in a QWERTY world. So those of you, some more geek humor. So those of you who have traveled internationally, though, or are from abroad, know that there are certainly differences in certain countries. Most recently, I was in France and sat down in the hotel's kiosk and got so frustrated because I couldn't find like the / symbol because it was in just a different place. But there's yet other keyboards out there. I just did actually a quick Google image search and found this one, which actually some of my more advanced friends have. It's this crazy looking thing, which frankly I can not even send an email effectively on. But it looks a little like this. And now frankly, the motivation, oh, laughing at me, huh? So frankly, they're actually, I mean, I don't mean to poke fun at these things because even I've had issues with RSI, repetitive strain injuries, that are actually can be alleviated to some extent by devices like this. But again, I just never wrapped my own mind around this. But the neatest keyboard I think I ever saw was owned by a really geeky MIT friend of mine in graduate school. And whereby in his lab, I sat down, went to just send an email or something, looked down at this keyboard, looked like a very standard black Dell keyboard, keys not like this, but a normal keyboard, but none of them were labeled. So there was no Q, W, E, R, T, there was no ABC, there was no labels on this keyboard. And it was frankly the most effective way I've ever seen of keeping people off your computer. Because but it was also this really interesting like intellectual challenge because it reminded me of that scene at the end of Star Wars where Luke kind of has to put away his machine and just go on faith alone. I mean, that's the only way I was able to type. I couldn't look down and type my email. I had to just literally like close my eyes and do it rote from memory. And I actually got through it. But it was the neatest thing I think I've ever seen. Better yet, I've also seen online keyboards that are optimized for moving the letters around just to mess with people. So even though it's actually a normal keyboard, people don't realize what the labels actually mean. So enough about that. In other news, if you haven't returned your scratch boards yet, I hope you're having a lot of fun with them. But please do return those to any of the teaching fellows in the corner here. We'll pretty much cut off that limit this week on Wednesday. And let's see. In other news about grades, so if we could pull up the lights for just a second. This I mentioned briefly at the very start of the term, but now that you've started getting official feedback from your TFs, it's perhaps worth a quick recap. I think 2 of the wheels are locked today. So this is essentially a summary numerically of what each page 2 of the problem sets convey qualitatively. So the teaching fellows have all been asked very expressly to focus this term, as in past terms, on as much qualitative feedback as possible and less on the quantitative feedback for a number of reasons, not the least of which it's far more educationally valuable to get prose comments back from a teacher pushing you toward how you might write better code, solve problems more efficiently, than just getting numeric scores that in and of themselves are not pedagogically that interesting. But I know there is a concern last semester, this semester, with getting things like 3s, because the mathematician in the room immediately does 3 divided by 5, 60% on my first problem set, and you get really frustrated or angry or disappointed or whatever the emotion happens to be. But realize, as these labels are meant to imply, the goal of the course in terms of grades at term start is to start off as many students as is possible and as is appropriate in this middle sweet spot, to be honest. 3 is good. 3 is not a C. 3 is not a 60%. You can do all the arithmetic you want, but that's not how we view these numbers. In fact, the TFs have all been asked very specifically by me to, keep their students as best as is possible, in this zone at first, so that there's actually room to grow. And frankly, even among those more comfortable in this room, odds are there's still plenty of room for improvement within your code, even though relative to, say, a complete noob's code, it might be better. But again, we ultimately consider students on an individual basis a term semester, so that, again, what's most important in this course is not so much where you end up relative to that person sitting next to you, but where you are relative to your other self. So do expect 3s in the beginning of the semester. If you're getting betters already, even if you got a couple bests here and there, outstanding. If you're in the 1, 2 range, take advantage of the innumerable resources the course offers, office hours and more. And do realize what these axes mean, if not clear from the PDFs themselves. So correctness really boils down to, does your program do what the spec told you it should do? Is it buggy? Is it bug-free? Does it behave as expected? Design is more of a subjective matter. And this is why we have humans grading your work and not just computers. We do use automated tools to assess, for the most part, correctness, because we can compare your output against some canonical output. But computers do not do a very good job at these other details. And that's why we have a team of some 30 teaching fellows. So design is about how well did you solve this problem? How clever was your design, or how clean was your design? If you have a perfectly functional program that's 100% correct, that doesn't mean it was designed well. You might have, again, loops and if conditions that are nested, this wide on the screen. There's probably an opportunity to fix that. Your program might be this long when really it could have been this long. Or your program runs in quadratic time when really you could have done the same problem linearly. So that's what design speaks to. And this is where the TFs on the PDFs and in emails are asked to provide as much qualitative feedback as possible. And style, frankly, is relatively easy. If you're losing points on style by semester's end, frankly, you're just throwing points away. And this is important. Naming variables appropriately, commenting your code, indenting properly goes a huge way long term, whether or not you're still taking courses after 50, just keeping your own code understandable by you. Even if I sit down a year hence and look at some of my own code that I've written, I have no clue what some of it does if I didn't actually take the time a priori to design it well. So think of style as something you should be doing as you write each and every line of code. Too often, it seems, do students relegate style to the very last minute. I'll comment it all later. I'll fix things later. That never seems to happen, right? Because 6:59 p.m. rolls around pretty fast, and that's the first thing to go. And it's the easiest thing, frankly, to fix. So don't do yourself a disservice with that. And if you have any concerns, by all means, reach out to me or your own teaching fellow or Yuki or Jansu throughout the semester. All right, so with that said, today is where I think things begin to get particularly interesting, because we can start to do more sophisticated things, both mechanically using various tools and also conceptually, because now we've gotten underneath our belts a lot of the basic building blocks we can now assume for the rest of the semester. Now, what do I mean by that? Well, the first thing we're going to introduce today is something called a debugger. So many of you have suffered bugs in your programs, and this is certainly to be expected. This is nothing that you ever move away from entirely. Certainly code I've written, whether it's for the bulletin board or even certain problem sets, have been erroneous sometimes, and you learn to get better at this. But thankfully, the act of debugging, finding bugs that you've made and fixing them, does not have to devolve to just thinking through your code or using printf all over the place, there are some powerful tools to help you help yourself. And the one we're going to introduce today is called Gdb, the Canoed Debugger. This is sort of the second nice counterpart to GCC, the compiler that you've been using. And it operates as follows. I'm going to go ahead and open a program called bar.c. It's among today's printouts, so you do have a copy of this. This program really does nothing interesting. In fact, it does a lot of unnecessary work, so bar.c. But I use this as an opportunity to walk through this program step by step, which is not something we can do just by running at the command line. I'm going to instead compile this program in a slightly special way and then run it within the confines of this thing called a debugger, a program that lets you pause execution anywhere you want, a program that lets you look inside of variables, look inside of arrays, see what's there, so you can do a little sanity check for yourself, and then you can let the program proceed. In short, with the debugger, can you walk through your own code step by step, or even jump around? And this is hugely invaluable, especially now that your problem sets are getting a little larger, because you can now diagnose problems a lot more easily. So this is, again, just a stupid program. Starts off in main. It calls a function called foo, which calls a function called bar. Notice at the top here, I've gone ahead and provided a prototype, as it's called, of each, so that GCC knows to expect these functions. But now I'm going to go ahead and compile this in a slightly different way. Rather than run GCC of bar.c, and actually I'm going to do -o bar, I'm going to add an additional flag that you may have seen flash across the screen sometimes, given how we've automated some tasks on nice.fast. But I'm going to go ahead and add to this a -gdb. So it's a little oddly named, but we'll be able to automate this before long. And what this tells GCC to do is, yes, compile this source code down to zeros and ones, called object code, but also include in a.out, or rather in the binary called bar, include some extra information that a normal human, a normal user, really doesn't care about. In fact, you're just wasting space by adding this special stuff to the binary. But include debugging symbols. Include some hints from my own source code so that I, the programmer, can walk through this code and actually see what's going on. So what I'm now going to do, now that I have a program called bar, as usual here, looks the same, I'm going to run gdb of bar and then hit enter. So I get a bunch of copyright stuff, not all that interesting. And then I get a GDB prompt. Now, the simplest thing I can do, and if we'll refer you online to a really nice cheat sheet for GDB, but there's a couple things that might be worth jotting down for yourself today, just so you don't forget. But run is perhaps the easiest command you can type at the GDB parenthetical prompt. Starting program. Incidentally, this is a longer path than you might be familiar with, but if you recall from earlier problem sets, nice.fas has big hard drives with lots of people's data on it. This is the full path, the number of steps it takes to find your directory from the root of the hard drive. And this is just being ever more explicit as to where I am. So not that interesting, except that I am, in fact, running bar at the very end. And apparently, this program just prints out something like world high on bar. So again, uninteresting, and it exited normally. But now let's see if we can step inside this thing. And incidentally, what do you think it means for a program to exit normally? How does GDB know that it exited normally? Yeah, so return 0. So finally, that detail we've been telling you is a good thing in many contexts to do is actually becoming useful, because now when we actually care about the correctness or the incorrectness of my code, getting back exit codes like that is helpful. So you know what I'm going to do? That happened way too fast, right? I'm not yet actually controlling this program. I'm going to go ahead, and incidentally, when I clear my screen, it's usually Control L, another little Linux trick. So Control L cleared my screen. But this time I'm going to say this: break in the function called main. So I'm going to hit enter, and now I get a slightly esoteric comment back. Breakpoint 1 at 0x8048505 file bar.c line 21. All right, so some of that's confusing, but this part's pretty clear. I just set what's called a breakpoint in the file called bar.c at line 21. And as the word's own name implies, a breakpoint is a moment in time or a line of your code that the GDB debugger is going to stop executing for a moment so that you can start to poke around. And only once you say, OK, I'm done poking around, will GDB continue executing your program. So now when I type run and hit enter, I get this. Breakpoint 1 main at bar C colon 21. So again, a little arcane, but just useful information. I now know where I am in my program. So this indicates my line number. This indicates what's on that line number. And if I do a little sanity check, you can type list to see the lines of code nearby where you just broke. OK, so line 16 was the return value for main. Line 17 is main's prototype here. Line 18 is this curly brace. I seem to have used tabs accidentally in my version of this. Your printed version should be fine. So ignore this white space for, let's actually fix this so there's no unnecessary confusion. OK, oops, GDB, whoops, GCC, GDB, break, main, run. OK, back where we were. Can you compile your code that fast? OK, so now I type list. Now my code is prettier. OK, so now there's no stupid distractions. OK, so we're on line 21. Now, why did the program break on apparently line 21 instead of, say, 19 or 16, which really seem to be the first lines? What is it actually breaking on? You can think back to some Scratch terminology. What construct is it actually breaking on when I say break main? Well, what's line 21? So it's like the first statement, right? It's an assignment statement. I've got a left-hand side thing, char star s equals hello world, whereas the stuff up top, these are just variables declarations or an arrays declaration. So you really don't see anything happen when you declare a variable, but you certainly will see some stuff happening usually when a statement is executed. So typing break main simply broke execution at line 21. So what does this mean? Well, nothing has yet happened in the world. In fact, what I can now do is type in print. And as the word implies, it's going to print something. What do I want to print? You know what? Let me go ahead and print the value of a. I'm just curious. What is inside of a? OK, that's weird. What is with this complete nonsense inside of a? Sorry? Louder than murmurs. What is this weird value? 134514073. Exactly. Good. So we did offer some caution a week or two ago when we said it's fine to declare variables, but you should never start using them until you yourself have assigned them a value. It might be nice if ideally variables all initialize to some value like 0, which actually is the case sometimes and in some languages. But clearly here, there's just some garbage value inside the variable called a. And that's because, again, a program has a whole bunch of RAM allocated to it. It can do anything it wants with that RAM, or you can, but it doesn't necessarily clean up that RAM. It doesn't initialize it necessarily all to zeros. And so, yes, I have a 32-bit chunk of memory called a. It's designed to store an int, but I haven't actually initialized it to something. So what's inside of a right now are the bits that previously belonged to some other variable or some other entity in this program. OK, so that's fine. That's not such a big deal. But I don't want to use a for any reason. And just as an aside, the $1 here, this is just a GDB thing so that you can actually reprint values from earlier. That's sort of like a temporary variable that, for now, just turn a blind eye to. But it can be useful. All right, well, what about b? Let me go ahead and print. Let me go ahead and print b. OK, interesting. So b is an array of type int of size 5. And apparently, I have 5 bogus values in there. What do those numbers mean? Well, frankly, who knows? But again, I haven't initialized that array to any specific integers yet. So I just have some junk in there. So what's neat already about GDB is that we're literally looking underneath the hood at what's going on inside the computer's memory. And unfortunately, nothing interesting just yet. What about s? Let me go ahead and print s. OK, that's really weird. So what is that? So there's some kind of an address. Anytime you see 0x starting today, that's going to refer to some kind of memory address, some location in RAM. What all the letters mean we'll determine in a moment. And then in the quoted string, that is definitely not hello world. Right? It's sort of like the ROT13 version of hello world. But even then, it's kind of garbage. But why is that? Why is there junk inside of s at this moment in time at line 21? All right, so it hasn't actually executed yet. When I've broken at line 21, I've broken before line 21 is executed. So if I actually want to step over to the next line, the command in GDB is next. So now I've advanced to line 22. This means line 21 has hopefully executed. So if I type the very same thing again, print s, aha, there is in fact my hello world string stored inside of the variable called s. And char star, that's synonymous with what little shorthand in CS50's library? It's just a string. Okay, and we'll tease apart what that asterisk is exactly doing for us later today and Wednesday. All right, so what comes next? I do a printf. Well, what is this all about? Well, print, let's see, s bracket 7. This is something we'll spend some time on. But if I go ahead and hit next, let's see what gets printed next. OK, no pun intended there. So line 22 is about to get executed when I type next. Here we go. OK, so world printed out. Now, why is that? Well, let's see. What I've just done is print ampersand s bracket 7, close brackets. So some new syntax. But just as a teaser so far, what is 7? Well, let's see. Here's s from here left to right. So this is 0, 1, 2, 3, 4, 5, 6, 7. It looks like when you start counting from 0, 7 is the index of the W. And we'll see later today and Wednesday what it's doing for us by adding this ampersand. Apparently, it's somehow tricking printf or compelling printf to print what string exactly? So world, clearly, because right, even though there's a lot of intermingling here of Gdb commands and output to the screen, it printed world. So somehow or other, this little trick of using ampersand s bracket s is going to the 7th location and then printing the substring that starts there. So we'll see why that actually works. OK, I'm getting a little confused where I am, so I'm going to type list again. OK, there I am. So here's the nearby lines. I'm on line 23. So if I type print A is still a bogus value. Let me go ahead and type next, and now print A. OK, now A is initialized to 5. OK, so just baby steps thus far. But you know, I'm kind of curious as to what foo is going to do now. So line 24 is the next line to be executed. Here it is in my list of code. If I just type next, unfortunately, it steps over foo, it executes it, but then it goes to the next line after foo. And the next line after foo, of course, is line 25, where I'm returning 0. So if I hit next one more time, next one more time for the close brace, voila. So apparently I'm actually in someone else's code. Whoops. In someone else's code. Typing continue is just going to finish off the program. Just go to the end. I've lost interest in this problem. And it exits normally because it, in fact, returns 0. But let's dive into foo again. So let me quickly pull up the code, since I know we're going back and forth a lot here. So this was main. We stepped all the way through main. But when I typed next at this line here, it went over it. It did execute it. But I'm really curious to see what's going on inside of foo. So let me do this. I'm going to rerun GDB on the program called bar. I'm going to hit enter. And you know what? I'm going to, again, say break main. You know what? I'm tired of seeing line 21 execute. Instead, I'm going to do this. I'm going to hit delete to delete all my breakpoints. Another little trick. And I'm going to say break in bar.c line 22. I really don't want to see line 21. I want to start at line 22. So you can exercise some precision. You can specify not a function's name, but a file's name, colon, line number to start right there. OK, so now let me type run. So I'm breaking at line 22. Line 21 and prior have all executed. It's just I have not broken execution until this point. I'm going to go ahead and click next, next. And now I'm going to type step. So next takes you over a line while still executing it. Step steps you into the line, which means step into this function. So now notice I'm inside a function called foo. N is referring to what exactly? So that's its parameter. Let me pull up bar.c. Here we go. So here is the prototype, or here's the declaration for foo. Returns an int. OK, here it takes a parameter n. So what I'm seeing in GDB is the parameterization of this function. So again, let me restart this. I'm going to go ahead and type run again, which will restart the whole thing. Enter. I'm at line 22. Next, next, and step. And now, OK. So the very first line of foo, per your printout, says to declare a variable b, and then assign b to n, and then multiply b by 2, and then call bar, and then return b. So you know what? If I type next, that's going to execute line 33. And then line 34, well, let's do a quick sanity check. If I type print n, what should I see? What was passed in as the value of n? OK, it was 5, right? Because a was 5. We passed in a to foo. N takes on the name, is the name we give to the parameter. So it too says 5. And now if I print b at this point, another little sanity check. So b gets n, and then b star equals 2 should give me what here? Yeah, so just 10. You know, I'm getting tired of these long commands. P, B, will also print. So there's a lot of little shortcuts where if you just write the first two letters, that's enough to tell GDB what to do. So finally, if I type step, I'm now going to step into bar. Bar doesn't do all that much. So in fact, as soon as I type next to go to line 42, it prints it. I'm now done with that. And now I'm losing interest. I found my problem. I'm just going to say continue. And it finishes along its way. So this in and of itself was just meant as an exercise in stepping through code. We'll soon start using this as a technique to fix problems in our code or understand what's going on. And this is going to be one of the hammers we have to hit all the time. When you start attending office hours or tackling bugs in your own code, do not underestimate the value of GDB. Inevitably, it'll be Tuesday, Wednesday, maybe Thursday night. You just need to get past some bug, and you're not going to want to sort of futz with a tool like GDB because it will cost you initially an extra 15 minutes, maybe an extra half an hour. It will save you hours by semester's end. No joke, leveraging tools like this. So don't dismiss it as something that was kind of interesting, but over my head. It's quite a powerful thing. All right, so with that said, let's now introduce or talk about some of the things we've been taking for granted. So this was an example from a while ago, Buggy3.c. We've included it again in today's printouts, but it was wrong. Right? So a couple of weeks ago, we tried to swap two values using a function, and it just didn't work. So what was the fundamental problem with this code? Sorry? Scope. So there was this problem of scope whereby when main called swap, passing in, I think the variables were x and y. So x and y were passed in, but copies of x and y were passed in. And so swap has a and b, which are identical to x and y, but they're copies. They're identical in the sense that they're copies. Did those 4 lines of code inside the curly braces actually work? Yeah, so they did work, right? That is a correct logical way of swapping two values. But unfortunately, the moment we got to the end of this function, what did we do with the values a and b? So absolutely nothing. So this, again, was Buggy3.c. Here, again, was the code. And just to be clear, if you think back to what memory looks like inside of a computer, memory looks like inside of a computer. Every time you call a function, it gets a frame on the so-called stack. It gets a chunk of RAM devoted just to it. So inside of this chunk here, inside of main, there apparently are two variables called x and y. So what's going on inside of memory here, if I can borrow this board for a moment, and I'll rotate it in just a second. So inside of main are two 32-bit chunks of memory. All right, so let's see. If we draw this as our RAM, this sort of big rectangle, down here is main's frame. So I'll label this as main. And carved out for main is, say, 32 bits here called x, another 32 bits here called y. And we've put inside of this RAM two values, the number 1 and the number 2. OK, so this is main. But then main calls swap in this implementation. Swap itself takes two arguments, two parameters called a and b. And per our picture here, what you get first on the stack is a frame containing a function's parameters. And then on top of that is another frame containing any local variables that it might have. So let's see what this translates to here. So now I've gone ahead and called foo's parameters. So we'll call this foo's params, albeit illegibly. And what goes inside of here? Well, I've passed in, or rather I've defined a and b, which are another 32-bit values. And what's going inside of them? Copies, 1 and 2. Now, what is this? Well, it's just kind of nice to be able to draw a whole rectangle. But this is unused space for the moment. So you can think of this as either being there or not being there. It's just being unused right now. All right, so what happens next? In the swap function, per this, int temp. Where does int temp go? Yeah, so it goes on its own frame, right? So above a function's parameters goes the memory being used for the function itself. So this is foo's own frame. And so foo now has a 32-bit value called temp. And initially, it's got some garbage value like 4, 5, 6, 7, right? Just because, right? We saw garbage values with GDB. Who knows what's in here at the moment in time when this line of code here is executed? All that's done is that 32 bits are set aside for temp. But as soon as I do temp equals a, what happens is that garbage value gets overwritten with something useful. So now we have that state of the world. The next line of code that gets executed here is this one. So we have A being assigned the value of B. So what happens here? Which of these 5 boxes changes? So just A, right? So this 1 gets clobbered and becomes a 2. So that is now the state of our world. And then finally, B gets temp. So that means I'm going to copy temp down to B. So now I have this state of the world. So in fact, this code is really, really correct. It has perfectly swapped these 2 values. It did cost us something, cost us 32 bits in the form of temp. But now the moment we hit this curly brace on the overhead, what happens? Yeah, so this goes away. And now technically I could erase this, but we'll discuss this in the context of forensics. Technically, this 1 does not go away. We just forget that it's called temp. So where do these garbage values come from? Well, henceforth, the next time we call a function, whoever gets allocated this 32 bits is going to have a garbage value of 1 because it's just been left there. But conceptually, this frame is thrown away entirely. And so now the state of my world is this, but then the function is in fact returning. So this now goes away. And unfortunately, all of that very correct, quote unquote, code was completely for naught because we did nothing with those values. And the reason for it ultimately was that variables, when passed from one function to another, are often, or at least by default, passed in by value as copies. So let's do a quick sanity check here. So that was called Buggy C. So I'm going to do make Buggy 3. And now notice as an aside, all this time when you type make, you do get this really long line. But we sort of anticipated this. So notice anytime you run make, automatically does -g GDB get inserted for you, just in case you actually want to poke around your own code. Now, as an aside, it's not a good thing to ship or sell software that has debugging symbols enabled. Usually something like this can actually be used by adversaries, by hackers, by bad guys to actually, crack your software, disable serial numbers, because it's more information than a user needs. But for you, the developer, it's actually very useful. So let's go ahead and now run GDB on Buggy 3. Enter. OK, a lot of copyright stuff. Let me go ahead and type run. Oh, right. Doesn't work. So I want to poke around. So let's do, what should I type? How do I poke around? OK, break main. Sure. All right, it's a short program. Won't be hard to go through it. So now I type run. All right, so I'm in main. OK, so I'm tired of typing next. I'm just going to hit n henceforth. So n, 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 n. It's the same program. Here's where it's interesting. So a quick sanity check. So I'm going to display x. I'm going to display y. So whereas print displays a value once, display should keep showing it for us. So if now I do step into swap, I'm going to be not in that case. Ignore what I said about display for a moment. Now inside of swap, what was passed in is a copy of x and a copy of y, currently called a and b. So if I print a and I print b, sanity check checks out. If I print temp at this point, what should I see? 0. Why 0? Just kind of because. It's a garbage value. There is sometimes some initialization that happens. So sometimes you do get 0 values, but you should never assume it. But if I do type next and now print out temp, aha, there is the value 1, which I explicitly put there inside of my swap function. So let me go to the very bottom of this function. A gets B, B gets temp. Okay, there's my curly brace. So let me check. Print A should hopefully say 2. Yep. And print B should say 1. It did, in fact, work. But then as soon as I continue to the end of my program, x and y are obviously unchanged because of the pictorial that we had there. All right, so GDB didn't help me solve a problem here, but it did help me see what's going on underneath the hood. Now, when I ran, let's tease one thing apart. When I ran GDB on bar a moment ago and set a breakpoint in main, I got this cryptic thing. So I said this was an address. What does that mean exactly? Like, what a address of what? Where? What context? Anyone? So murmuring doesn't seem to help today, so we'll do this approach. Or I'll just stand here awkwardly. Anyone? Yes. Yeah, so it's a location in memory. What kind of memory? Not hard disk, but RAM. So if, again, we model our RAM, model our world of memory as this rectangle, right? Thus far, we've just been drawing nice little boxes that look kind of like squares, and we assume that a square is 32 bits. But you need to be able to address memory somehow. So in fact, what really a computer does is, yes, it takes your RAM. Maybe it thinks of it kind of as this conceptual rectangle, but it's got to number every location in this rectangle. So this chunk of memory here, even though I've labeled it X and I've labeled it Y, those actually have numeric addresses. So technically, this box here is numbered 0x123. And then this box here, well, actually, let me pick an easier number. So let's suppose this is 0x12. That just happens to be the address, the byte. So if you've got 2 gigabytes of RAM, you've got 2 billion bytes of RAM. This happens to be byte 12, albeit in something called hexadecimal. So what's the address of Y going to be? OX1, just take a guess. So not 3, because how many bytes away is this guy? It's an int. So an int is 32 bits. 32 bits is 4 bytes. So that means if this is OX12, this is going to be OX16. All right, so all that minutia from week 0 when we talked a little bit about binary and bits, it's actually useful because now it applies to the addressing of memory. Now, as an aside, and I think we said this once before, there are many operating systems, some of which you're still using, that can only use, say, 2 gigabytes of RAM. Why might that be? Why 2 gigabytes of RAM? I think XP is limited to this, maybe 3 gigabytes of RAM. Yeah? So there's a limit to how long those statements are. Yeah, so, but put another way, when we say a computer is a 32-bit computer or 32-bit CPU, as we've said, that just means that inside of the CPU is memory called registers. 32 bits are used to represent numbers. Well, the biggest number we can represent with 32 bits is 4 billion. But if we use positive and negative values, the biggest number we can represent is 2 billion. And so why can some computers, some operating systems have a maximum amount of RAM at 2 gigabytes? Well, that's 2 billion bytes. Well, if the programmers of that operating system or the designers of that CPU only used 32-bit values to implement numbers, how can you address the 2 billionth and 1 byte up here if you literally cannot count that high using just 32 bits? Now, thankfully, the world has moved to 64-bit computers, 64-bit CPUs, which means you can have a ridiculous amount of memory. So this was just kind of for historical reasons or short-sightedness that we have some of these constraints. But that's what it boils down to. You can't use 3 gigabytes or 4 gigabytes or 5 gigabytes of RAM in some computers, even though that's really useful for things like Photoshop these days because your ints are not big enough. They once were, but no longer. All right, so how do we then start counting in this new scheme? All right, well, we know binary, zeros and ones, and we know decimal. Let's see how we can get from zeros and ones and zeros through nines to OX and these other letters here. So in binary, what's the number for 0 using 4 bits? Good. All right, how about 1? OK, and then whoops, that. And then 1, whoops, 1, 1. And this is, I'll put some little reminders here if this has been a while. OK, so now 0, 1, 0, 0 is 4. 0, 1, 0, 1 is 5. 0, 1, 1, 0 is 6. 0, 1, 1, 1 is 7. Let's see, haven't embarrassed myself yet. 1, 0, 0, 1 is 9. OK, fun part coming up. 1, 0, 1, 0 is 10. But if I'm using the decimal system, the only digits I have for numbers representations are 0 through 9. So yes, I can compose 10 by using a 1 and a 0. But if your notion of a digit is a single number, so 0 through 9, we have no way of expressing the number 10 using individual decimal digits. But fortunately, there are other base systems. We talked about binary. We talked about decimal. There's also something called hexadecimal, whereas in binary, you have 2 values, 0 and 1. Decimal, dec, you have 10 values, 0 through 9. Hexadecimal, you have 16, 0 through 9, and then A through F. right? So the world needed to count a little higher than decimal allowed using individual digits. So now 1, 0, 1, 1 would normally be 11, but I can't do that because, again, 11 is not a digit. It's the composition of 2 digits. The single digit I'm looking for in hexadecimal would be B. And then finally, 1100 is C, 1101 is D, 1110 is E, and then, thankfully, no mistakes, is F. And the context, frankly, that some of you might have actually seen hexadecimal before is in kind of a silly context, making web pages, where color codes are often represented with hexadecimal these days. So anytime we need to count a little higher than decimal allows, and certainly higher than binary, I mean, my God, this would be a nightmare if GDB told us where things were in binary. It's not very human-friendly. We can now at least count up here in week 4 to the number 16 using this new base system. But this is useful because many, many, many programs actually use hexadecimal to represent values here. Now, it's not going to be that useful to you generally to know where in your computer's RAM your function or your variables ended up. But sometimes it's useful to care about maybe the last couple of digits, because then you kind of know where they are relative to each other in what's otherwise a really big address space. And when we get to our forensics problem set in a couple of weeks' time, and you actually have to recover JPEGs from disk, what you're going to be seeing when you look at the files on disk are actually not numbers like 0, 1 through 9, but rather you're going to see hexadecimal, partly just by convention. Because what is one upside of using hexadecimal instead of, say, decimal? What's useful about it, even on first glance? Like, what is the value of defining A through F in this way? It's shorter. That's it, right? You can express more values using just individual digits. So there's an efficiency aspect. And consider, too, the whole reason we use decimal as humans instead of binary is, my God, just to represent the number 15, look how many digits. Well, maybe that's not that compelling. You have to use 4 digits, and we can use 2 to represent the number 15. But if you think a little further out, this actually does have ripple effects with much larger values, though that might not have been compelling. OK, so that was a lot all at once. Why don't we go ahead and take our 5-minute break here? All right, we are back. So it occurs to me that I might have induced some fear by saying you shouldn't be getting many 1s and 2s. So on the first C problem set, you should have gotten some 1s and 2s because design and style, as your TF may have told you, were only out of 2 possible points. So you probably did get a 1 or a 2. And the motivation, normally everything will be out of 5 points. So that little chart I drew on the back of the board is applicable. But in the beginning of the semester with Pset 1, when we've barely had time to talk about what design is, what style is, we certainly don't want to put you at a disadvantage by expecting more than we possibly could. So 1s and 2s, very good on problem set 1 for those 2 axes. So the setup here was that swap has not worked for weeks. Like, we've been able to implement functions. We've been able to take in inputs, produce outputs. But swap itself cannot swap 2 values successfully. So one approach, at least instinctively, might be, well, maybe the problem is this whole time swap has been a void function. We are not actually returning a value. So could we, in fact, maybe start returning a value? So if I call swap and pass in 2 values, maybe I could return the swapped values. But there's a problem here. How many values can you return from a function as far as we've seen in C? So only 1. So we could maybe we could pass in, we could do something like this. I might be able to do, so int x gets 1, int y gets 2. Maybe I could do something like x gets swap, and then I can pass in x comma y. OK, so that could, in fact, swap x. But now, odds are this would not work. Right? Well, I could kind of hack this, right? I could do swap yx. Right, if you kind of think how I might implement it, you could kind of hack this together. This feels kind of stupid, right? Or if you're still kind of acclimating to what we mean by good design, probably not good design here. So it would be ideal if we could just return 2 new values. Give me back 2 values, and then I'll assign those to x and y. And you can do this in some languages, but not in C. So the approach that is almost always taken that actually opens the doors to some really powerful, if dangerous, code is this one here. Thus far, we've been passing in arguments by value, by copy. By contrast, there's something called passing in arguments by pointer, or passing in by reference. So pointer, reference, synonymous. Value, copy, synonymous. So passing in by pointer does something fundamentally different. Instead of passing to swap the values of x and y, you can use this asterisk notation and pass in not the values of x and y, but their physical locations in RAM. Now, as soon as you pass in the locations, aka the addresses of two variables in RAM, you're essentially handing a function like swap the power to do anything he wants to those variables. Because if you tell swap where x and y live in memory, he can go to town on them and swap them, change them, delete them, overwrite them, anything that function wants. Now, hopefully, you're writing the function and you're not going to mess with your own variables. But what this is going to do for us is the following. If in main, I have the following scenario. So here, we'll say as my RAM again. And in main, we have main's arguments like argc and argv, which aren't interesting today. And then we have main, which has this. We have a value of x, and we have a value for y. And these numbers are 1 and 2. So hopefully you can see this. We just have two little boxes, the values 1 and 2. And these have addresses. So let's just use the same addresses as before. So the address of this thing for reference is 0x12. That's completely arbitrary. I just made that up. And the address of this thing, completely arbitrary except that it's nearby, is 0x16, which is 4 bytes away. So I'm being consistent relative, but the starting point was random. OK, so that's what I've done here. If I now call swap, before I allocated 32 bits, and passed in the values of 1 and 2. But you know what? Let me do this. Let me call swap this time. I'm just going to label it over here. So this is swap's parameters. And I'm still going to call these parameters A and B. But you know what? What am I going to pass in as A and B? Not 1 and 2, but what numbers? Yeah, so 0x12, and I apologize for my handwriting. We'll clean this up in the scribe notes, or 0x and 0x16. So now, incidentally, 0x, this is just human convention for the following is a hexadecimal number. That's it. It doesn't mean there's a 0 there. It doesn't mean there's a digit x. It just means the following digits are hexadecimal. All right, so now I'm passing in this address and this address. So this means swap can now use that information somehow. So how do you do that? Well, here is the new and improved and finally correct version of swap. What we're doing now with swap is the same thing as before. We're declaring a temporary variable. So that was swap's parameters. Here now is swap's other frame where he can actually put local variables. So here's a local variable called temp. Now, what I don't want to do is do temp equals a semicolon. I don't want to just copy the value of a into temp because I don't really care fundamentally about the address of a. I'm just going to use that as a little shortcut to actually getting at a itself. So the notation for following a pointer, the notation for going to an address and getting the value that's at that address is this asterisk before the a. So this is the so-called dereference operator. It's just a star, just an asterisk. But what this tells the computer is treat a as a pointer, an address. So a pointer is an address, a location in memory. Those two are synonyms henceforth. Go to that address, get what's there. And what is there? What's at star a? 1. Go to the address A, get what's there. This is the address A, 0x12. Get what's there, which is 1, and put 1 where? Inside of temp. So that's it. So new syntax, but it's relatively simple. We just have now introduced the idea of describing data not just by its names, its labels, the variable names like x, y, and a and b, but we also have now another sort of more advanced way of getting at data by way of their actual addresses in memory. And this is where C is both powerful and dangerous. A lot of modern languages do not let you get this close to the hardware. They don't let you get this close to manipulating computers' memory because you can do a lot of damage relatively easily. And we'll do precisely that in a lecture to come. But for now, it's very powerful because we can really do anything we want underneath the hood, which in this case is advantageous. So what do I do next? I've now copied the value 1 into temp. So we're good. We're on our way. Now star A gets star B. All right, well, let's tease that apart. Let's start with the right-hand side first, star B. So that means treat B as a pointer, OX16. Go there. Well, where is OX16? Well, my dotted line says it's right down here. So go there, and then star B in the end is equivalent to what value? 2, right? Just get the value 2. What do I do with the value 2? Well, assign it to the left-hand side. What's the left-hand side? OK, same idea. Treat A as a pointer, OX12. Go to that address. So follow the pointer, and then put what there? 2. That's it. All right, so go there. So it's kind of like there's this intermediate step. We now have to go to an extra location. We have to do a little more work mentally and also programmatically. But the end result is still going to be the same, but in a much better way. So now what do I do? So star B gets temp. Well, temp is easy. This is the name of a variable. Bam, I'm there. This is like week 1 stuff. Now what do I do with temp? Go to the address pointed at by B. All right, so B is this. This is a pointer, OX16. Star B says go there. Where? Here, that is OX16, do what with it? Put there what value? 1, aka temp. And so now, even though I've used the same amount of memory, I've still got 2 parameters, I've still got a local variable, notice what I've done is not change the local variables, which was really just a mistake last time, really didn't get us anywhere. What I've actually used, those 2 parameters, is as little shortcuts to go to the location in RAM, to go into main's own frame, and change the original values. So when I run this version here, swap.c, hopefully, finally, all these weeks later, well, I get a correct answer. So it's the same exact function. The only thing I've changed is the implementation of swap, but I've taken care to do 2 things here. Actually, I did 1 change in main. Notice what I've done. I did all the stuff we just described, the star notation. And for now, this is the dereference operator. It means go to this address. OK, what did I also change in swap, though? Something I didn't yet mention. No, so what did I also do in swap? Not ampersand. What else has changed vis-a-vis the Buggy version? Well, this part, so not ampersand, the stars here, right? So the declaration of swap has changed ever so slightly. Previously, the declaration of swap, remember in the broken version from just now and also a couple of weeks ago, was this: int A, int B. And that's great. I took in 2 ints, but they were copies. So if you instead want to pass by reference, pass by pointer, you instead say, you know what? Here comes not an int, but a pointer to an int. Here comes the address of an int. And the way that you express the address of something is to put a star in front of it. So same symbol, which is a little confusing, slightly different meaning inside of this parenthetical context versus inside of the function itself. But this just means that swap takes 2 arguments. One calls A, one called B, and both of them happen to be the addresses of integers in memory. And that's precisely consistent with this picture. So I have changed one other thing, as a couple of people noticed. What has changed in my main function, apparently? So there are these ampersands, exactly. So the ampersand operator is kind of like the opposite of the dereference operator. Whereas the star inside of swap says go to this address, the ampersand operator says get the address of the following variable. So previously, in the Buggy version of my main function, I just did this. I passed in x, I passed in y, but that was problematic because I'm saying here swap, here's 2 values, 1 and 2, do what you want with them. But do only what you want with the copies that I'm handing you. So in this case, when I say ampersand x and ampersand y, this is saying, hey swap, here comes the address of an int. Let's call it x. I'll call it x. You can call it anything you want. Here comes the address of another int. I'll call it y, but you can call it anything you want. Say b. Do what you want with these now. So you're now handing to swap, again, the power to actually manipulate the data at those locations. And this is hugely powerful. In fact, we've seen this before. Where have we seen this star operator before and not in the context of multiplication? What data type? So right, we've seen it in argv. So we've had char, star, argv brackets. So we've seen the asterisks there, and it's clearly not multiplication there. We've seen that char star is synonymous with string, and that too has nothing to do with multiplication. So we've seen this before, but because now things are getting a little more sophisticated, a little more interesting, do we finally started addressing, pun intended, what that symbol actually means. So pictorially, we offer this. So there's a nice tutorial linked on the resources page of the course's website from How Stuff Works. And it's actually got a nice exposition of what's going on inside. And their pictures are much cleaner than mine. So these two lines of code, int I, comma j, and int star p, declare a picture like the following. So what's going on here, and I'm going to go ahead and eliminate this. It will appear on the scribe notes if needed. And let me go ahead and see if we can't relate this to the previous stuff. So int I, comma j. Well, we've done stuff like this before. Int I, comma j. And I've even drawn silly little pictures like this. What does this do? Well, this allocates somewhere in RAM 32 bits, and it calls it I. And then another 32 bits in memory calls it j. They're not necessarily next to each other. Odds are they are if you declared them one after the other. But there's no guarantee of contiguousness unless you've declared an array. But I've just declared two ints here, I and j, so I get two chunks of RAM. Now, if I do something like this, I gets, let's say, 3. What happens in my picture? Well, 3 goes there. And what's here? Well, this is some garbage value. Who knows what's there? We better not do anything with it yet. All right, let me do something else kind of random. So j gets 4. All right, what happens? Well, this unknown value now becomes a 4. Now suppose I want to change the value of I. The easiest, most obvious way of changing I from 3 to, say, 5 would be this. I gets 5. How does the picture change? Well, the 3 becomes a 5, right? Very much week 1 stuff. But let's see if we can't now leverage this idea, albeit in a little sandbox, to use the address of this thing. Suppose I want to change I from 3 to 5, but I want to kind of impress people and do it in a manner that leverages the addresses of this stuff. Well, what this slide here, what this picture and tutorial are explaining, is that just as you declare an int just by saying int and then the name of the thing, you declare a pointer to a data type by saying int star p. So this now declares, and for those for whom this might be cut off, I've just written int star p semicolon. All this is doing is saying to GCC, you know what, give me 32 bits, but I'm not going to store in those 32 bits an int, but rather an address of an int. And it just so happens that with what data type our address is actually stored, have we been saying? With ints. So in this case, it's actually kind of a coincidence, but a pointer, as this thing is called, the address in a C program is implemented ultimately by way of an int. So this is going to be another 32-bit chunk, and that's why I'm drawing them all as roughly the same size squares. Here is its name p. And if I now say this, let's say p gets I, what would that do for me? P gets I. So nothing. Bad stuff, right? Because I'm saying store in this address, store in this variable I. Well, what does that mean? Well, that means put 3 here. But the compiler is probably going to yell at us because these two things, p and I, are of different data types, right? This is like trying to cram one data type into another that doesn't really belong there. P is supposed to be the address of something, but I is not the address of something. I is a value. So if what my real goal was here is not to store in p the value of I, but the address of I, what did we just say is the trick syntactically for that? Yeah, so p gets ampersand of I. And what that means is that what goes here is what? Well, gosh, now I have to make the picture a little messier. All right, so I don't know where this stuff is. So let's say it's in 0x123. It's somewhere in memory. And this one, who knows? This is in 0x789. Because again, they're not necessarily adjacent to each other. So who knows where they are? But in now this context, p gets ampersand I. What am I doing? Well, what is ampersand I? Ampersand I is the address of I, which I just said. And I'm sort of the omniscient God here who knows where stuff is in memory. I'm going to put OX123 here. Now, what you'll see in most textbooks, and frankly, even we, after this week, will start doing, because talking about arbitrarily picked hexadecimal numbers really is not intellectually enlightening. What we'll typically do is abstract this detail away and say, you know what? frankly, who cares where this thing is in memory? It really doesn't benefit us to know the specifics of that. We're going to exploit where it is, but we don't have to care where it is precisely. So what you'll usually see me and most any teacher or text do is draw a pointer, as an arrow. So what's stored inside of P is, yes, the address of I, but let's depict that. Let's convey that idea pictorially just by drawing an arrow. So what can I now do with this information? Well, let's see. If I do I gets 5, I immediately change the 3 to a 5. But what if I instead do star P gets 5? Well, what does that mean? Well, P is here. Star P means go to that address. So this sort of like Chutes and ladders style, when you say star P, go to that actual address and then do what? Then assign it the value of 5. So in short, a few new syntactic tricks. We've got ampersand to say, give me the address of something. Star means go here. Or in the context of a function's declaration, star says, expect not an int, but a pointer to an int. So the meaning of the star is somewhat context sensitive. But at the end of the day, anytime you see the star or this ampersand operator now, odds are we're actually talking about these things called pointers. And again, a pointer is just a fancy way of saying the address of a piece of memory. OK. Any questions about pointers? No? OK. So this, and again, I can't emphasize enough, if this feels a little new, these pictures are actually pretty good. But they just depict what we talked about a moment ago. So it turns out there is a relationship with arrays that we've kind of been waving our hands at. Clearly, argv has something to do with arrays, but also pointers because of the brackets and the star. And char star is the technical definition for a string. But we already know that strings are really just chars, but not chars per se, arrays of chars. So there's actually been this relationship between pointers and array, or at least a similarity between them. So just to slap a picture on this too, if in code I say int I, what I get at top right there is a 32-bit chunk of memory. The How Stuff Works tutorial says question mark, question mark, question mark, because who knows what's there? It's some garbage value. But that's how we might depict it with a diagram. Int a bracket 5 close bracket, in layman's terms, or slightly more technical layman's terms, that declares an array of size 5 for 5 ints. OK, what does that mean? Well, in memory, that means you get 5 chunks of memory, 5 32-bit chunks, back to back to back to back to back, as in the middle of this picture at top right. It's called a. That's the name of the variable. And a bracket 0 is the first location. A bracket 1 is the second location, on up to a bracket 4. But it turns out you can actually start to treat arrays in most contexts as though they're actually pointers. So even though in this context A is really just the name of this array, it turns out you can even in C say something like line 3 there. Int star P, which says give me a pointer to an int and call it P. What am I assigning it? A. So what do you think is actually getting stored inside of P per this third line of code? It's going to be the address. What is it the address of? Yeah, it's the address of the first element in the array, right? So there's an advantage of arrays being defined as contiguous blocks of memory. You might think at first glance, wow, if I've just been handed 5 ints, I better know the addresses of all 5 integers. Otherwise, how am I going to hang on to them? But really, you don't. If you know that the memory is back to back to back to back to back, it's not all that enlightening to know what the address of this is, this is, this is. All you need to know is where the starting point is. And then you, the programmer, hopefully kept around a variable like n, or just have some recollection of the length. Because if you know the starting address in memory and the length of the thing and how big each one is, you can reverse engineer the actual address of anything in between. So what's happening here with int star P gets A, this is saying store in P the address of the first integer in this array. Which means if I then proceed to do this, let me write one line of code on the fly with respect to this bunch of code. If I say print f, quote unquote, %d, and then bracket a, let's say, it would have helped if they gave us some values. OK, not the best example. What's this going to print? OK, so that's actually a good, clever answer. So the value in the first location of the array. Frankly, I realized this was a bad example because it's just going to print junk. Who knows what it's going to print because question marks are there. But at a higher level, this is going to print the first int in the array. But it turns out if I do this too, if I've done star p gets a, notice what happens. If I just put p, this is going to literally print the address, right? So ints, pointers are in fact numbers. They are integers. %d means put an integer here. So this would actually print the address of the first location in A, otherwise known as p. This would print the value inside p. But if you want to go to p and actually print that location, if I add this, it turns out that this is essentially synonymous with a bracket 0 at this point in the story. So again, I have this ability to figure out the address of something in memory. But then with the star operator, I have the ability to go to that address. So I now have a way of expressing the same values with different ways. And this in and of itself, not all that useful, because we've not given you a trick that you need to solve any new problems in a silly context like this. But we'll see that this is actually increasingly powerful. So let's take a look, actually. In compare1.c, which you do have a printout of today, we have now an explicit use of star. So now, at least in lectures, we're going to begin to take off the training wheels, so to speak. And yes, we're going to talk about strings, but let's really call them what they are. They are char stars, or they are arrays of characters. All right, so what does this mean? So here's a program called compare1.c. Per the comments up top, this is going to try and fail to compare two strings. But the interesting question is going to be why? Well, it's not a long program, so let's see what's going on. So here we have printf, so say something this program's going to do. Then I'm using getString, and I'm storing the string that's returned in a variable called s1. But again, training wheels off. I'm not calling it a string. It's a char star. Same thing, but now we can finally ask the question, what does that mean? All right, and then the line 3 here, say something else. And then I store the second thing the user types in s2. That's where the string's getting stored. But now let's push a little harder on my own language here. When I say getString returns a string, how do you return a string? Like, functions can only return one thing. Now, you can't just hand the user any number of characters, a whole sentence. What is getString really returning? So an array of characters, but what does that mean? What literally is being handed back? Because an array of characters still sounds plural. What's getting handed back? A pointer, the address of the string in memory. So all this time when getString has been getting a string from the user, what that means is getString, whose implementation we'll look at, is actually allocating a bunch of RAM, all contiguously. Any character I type at the keyboard as the human, as part of this function, gets stored here, then here, then here, then here, character by character. And then getString, which again we wrote in order to return that string to you, quote unquote, to return conceptually that whole string, it suffices to return to you what? Just the address of the first character in that string. And why is that sufficient? I don't know in advance how long that string is. But what did we say if briefly, a few lectures ago, demarks the end of a string in memory? So special 0 character. So if I type in the word foo at the keyboard, and the getString function, as we'll see, stores a character f, then O, then O. It also stores a special terminating character, which we represent with \0. This is literally all zeros. And this demarks the end of the string so that I don't have to know or guess what the length of the string is. If I'm given the address of the beginning of the string, I can figure out how long the string is just with a for loop. Check here, check here, check here. Aha. There's \0. So in fact, many of you have probably used the Stirling function for some Pset or another, string length, to get the length of a string. What is it doing? I mean, it is literally implemented with a for or while loop. It starts at the beginning of the string and just checks. Are you \0? Are you \0? Are you \0? When the answer is finally yes, it returns the number of times it asks that question. So that's all Stirling has been doing. So what this means is getString is going to return a pointer to a character that is a pointer to an array of characters. So why does the following fail? Notice this. If I get one string s1 and then get string s2 and then compare the two, this program's actually broken. So let me do this. Make compare1. OK, and now I'm going to run compare1. OK, I'm going to say foo and bar. And obviously, I've typed different things. And the program seems to be correct, at least 50% of the time. Well, now let me do this. So foo, foo. Maybe it was just Buggy that time. Bar, bar. Right? So maybe you've even done that too, right? Maybe if I just cross my fingers and rerun my program, the bug will go away. But it hasn't in this case. So what has happened? Well, let's see. We don't even know how getString is really implemented. Well, technically, you could look at the code you have printed, but there's a bunch of it. But we can infer what's really going on. So getString, again, is a function we wrote. Its purpose in life is to figure out what the user has typed at the keyboard and then return it to you as an array of characters. So what's happening the first time I call getString and I type in foo, getString is allocating, again, the thing I just drew, not 3, but 4 characters, because we need a 4th character, an extra character for the /0. What is it returning? It's returning to me the address of this thing, 123, we'll say. I don't know where it is. Who cares? It's just 0x123. But then the next time I call getString, I'm getting a different chunk of memory. So up here I did this. S1 gets, and this is char star, S1 gets getString. So what is inside of S1 at this point? Well, S1 is a local variable. It's of type char star, which just means it's a pointer to a char. What does that mean? After this line of code is executed, what gets put inside of this 32-bit chunk of memory? OX123. That's all it takes to store a string. Or really, that's all it takes to remember where a string is, because I can figure out where the string ends just by, again, iterating over it or calling the already implemented Stirling function. But now I do this. Now in my own program, char star s2 gets getString. Suppose I do type in the same word again, foo. Well, what happens? Well, getString, written by us, allocates another chunk of 4 bytes. FOO gets stored there, /0. I don't know where this is, like OX456. Who knows where it ends up? Now, what gets returned and stored in S2? Well, S2 is another pointer to a char. So this is called S2. And what goes in this box? Yeah, so OX, 456. So now, even if you're a little fuzzy today on what we mean by pointers, even this line should make some sense. If I then try to compare 2 strings by comparing their variables' names, does S1 equal S2? This is going to be false. Why? Even though foo is clearly equal to foo. Yeah, exactly. S1, S2, I mean, clearly not the same. You compare these for equality with equals equals, you're going to get back false. So that begs the question, how do you compare 2 strings for equality? Well, right, the wise ass would say call stircomp, which is a function that's already been implemented that does that. But how would that be implemented? I tried to beat you to it that time. Yeah, so really what we need to do if we want to compare 2 strings is something more like a comparison with this function here, stircomp, which how is it implemented? How would you, if you had to implement this function called stircomp, because it's string comparison, but it's the concise way of saying it, how do you compare 2 strings for equality, given the address of one and the address of another? Probably just some kind of for loop. Are they equal? Are they equal? Are they equal? If you ever answer no, what do you return? False. But if you then hit a null character, what do you do? If you hit a null character at the same time, rather, return true. Right? You can do this with a for loop, a while loop. You can just check for that character within a loop. So this new and improved version is actually correct. And I also did a sanity check. So getString, as we'll see in its documentation, can return this special sentinel value null, which means something bad happened. The user didn't actually type something, or the user typed a special sequence of commands that actually in many contexts could crash your program. So getString does return this so-called sentinel value called null in all caps. So what I actually need to do here, as we'll see as a matter of best practice, is always check the return value of a function like this. And if it does not equal null, that is, if there is actually a string there, OK, go ahead and compare the two with, go ahead and compare the two with this function called stircomp that actually returns a negative value, a 0 value, or a 1 value. And you can determine with that if they type the same things. What does get returned? You can infer this now using your deductive skills. What gets returned by stircomp if 2 strings are equal? 0. And why might you want to return a negative value versus a positive one? If it's less than or greater than, i.e. if it's alphabetically before it or alphabetically after it. So it seems here we have a little building block for sorting actual strings. More on that Wednesday. See you.